I'm Jeff Bodycomb with HORIBA, and today we have Ian Treviranus, also with HORIBA, who's going to talk to us about optimizing dry powder measurements. He's going to talk about specifically the LA-950 PowderJet. So with that, Ian, why don't you take it away?
Thank you, Jeff. Let me get my clicking materials and pointing materials all right. Okay, so as Jeff said, my name is Ian Treviranus. I'm going to be talking in general today about how we make the best possible dry powder measurements, and with a specific emphasis towards the LA-950 PowderJet accessory. My contact information you can see down here in the slide, and our particle size website you can get to very quickly by following horiba.com/us/particle. So a quick overview of what we're going to talk about today. Why should we measure dry? If you've never done it before, I'm going to give you a few good reasons why you might consider it. We'll talk briefly about sampling and dispersion, some unique PowderJet features to sort of help maximize precision and frankly remove a lot of headaches that have historically come along with dry powder analysis. And then we're going to go into a few case studies and some general discussion about method development. So right off the bat, we'll start about why should you measure dry? Well, the number one reason we see from people is that oftentimes it's difficult to measure wet. And that could either be through solubility concerns, maybe the material is so dense that you need to have the world's strongest pumping system to keep it in suspension. It could be just very expensive to disperse. A lot of times when you're dealing with certain particles, you need to buy very expensive dispersants or surfactant combinations, and it just quickly cost grows. And sort of along the lines of a dispersion problem, you could just very easily have a particle that begins to swell. You might also have a strong preference to measure dry because the final use of the particle is dry. Or it could simply be that you get more information out of measuring it in its native state than you would if it was in a wet dispersion. And one example there is if you had very weak agglomerates, and I'll define what an agglomerate is in a few slides, but if you had very weak agglomerates that you wanted to capture, it's very difficult to do that in a wet dispersion. You can do it in dry. So very quickly, here's the workflow of any dry powder measurement. You start off with some analyzer. This is the LA-950 with the PowderJet attachment. Some powder, clearly. Some mad scientist. This is either you or me. And then you get some results. And the goal of any particle size measurement, especially a series of them, is maximum precision. That's how we get reliability. It's how we can get some faith in the results. So now we're going to move on to sampling and dispersion. And this is sort of a classic slide you'll see from a bunch of particle size analysis folks. And really what it is it's describing where you're going to find the error in a measurement. So if you have very small particles, right, and so the x-axis here is particle size. We're increasing as we move along the x-axis. Small particles, most of the error comes from sample preparation, and most of the time this means dispersion. For large particles, most of the error comes from sample extraction. So how do you take your several hundred kilograms of raw material if you're a bulk manufacturer and get it all the way down to the 1 to 10 grams of material you might need for a laser diffraction measurement? Or if you're a if you're a formulator and you're only manufacturing 500 milligrams at a time, or synthesizing 500 milligrams at a time, that's not really an issue. But most of the time, the instrument error contributes a very small and relatively constant amount of error. So this is the sort of area we're going to be focusing on for the next few slides, sample extraction. And there's different techniques. If you want more information on the subject, I highly encourage you to take a look at our 5th bootcamp webinar. It's called Sampling and Dispersion. It goes into more detail. Grab sampling is something we probably all have done. I know I did it in the applications lab when I worked in there. And it's simply you have a bottle, you have a spatula, or some mechanism of grabbing the sample, and you just scoop out. So the worst type of grab sampling is where you just scoop from the top, and the best type is where you can guarantee somehow that the powder's well mixed and you scoop sort of from the center. None of it's great, and the problem with grab sampling is simply if you have a wide range of particle sizes in the sample, over time, or with some light to moderate amount of shaking, what it's going to appear is though the sample is segregating based on size. So it'll look like the largest particles are percolating upwards, and the small particles will compact into some denser configuration on the bottom. The example I usually give is if you watch The Price is Right, this is kind of like the Plinko game. You can think of the small particles as being relatively free-flowing, and they sort of bounce around in between the larger particles until they settle at the bottom. Nonetheless, it is the easiest possible method, and therefore the most well-used. Most used, not necessarily well-used, excuse me. And so here's the idea. You have a bottle. You might tumble it a handful of times and then stick the spatula in. Another technique is called chute riffling, and this is usually just a metal contraption where you're pouring your sample in, and depending on how the chute riffler is constructed, you might go into 4 different sample containers. It could be 8 different sample containers. You might have multiples of these at different sizes that are stacked on top of each other. And the idea is when you get down to the bottom, you have some tray that has hopefully a representative amount and size distribution of sample that you can then put into your analyzer. Better than grab sampling, but not as good as rotary riffling. Rotary riffling is what we do in our applications lab when we really want to remove sampling as a potential source of error. And the way this works, if you look down at the image in the lower right corner here, is you put your sample on the feeder tray, you turn on the feeder tray, it vibrates down, and you have all these little pie slices. In this image it's just holes, but the one in our lab it's pie slices. And this is spinning, so it's always spinning around. So it doesn't really matter if the particles on the vibratory feeders begin to segregate, if the large particles come off fastest and the finer, more cohesive particles come off slowest, because this is always spinning. And so at the end you have this pie slice that, depending on how much material is in it, you could just put one or multiples in your analyzer and call that a representative sample. Here is an often cited work where a sugar sand mixture was tested for accuracy based on different sampling techniques. And what we can see is that the scoop sampling, or grab sampling as I called it a few slides back, has by far the most error. As we move down to spinning riffling, we reduce the error by over an order of magnitude. If you'd like to learn more about it, you should look up a lot of things by Terry Allen. He's one of the wise old men of particle size. I'm going to quickly define what we mean by different dispersion conditions. So a well-dispersed material is one where primary particles, are not touching each other. They may be interacting with each other, but they're not physically that close to each other. Agglomerated particles is where they're sort of weakly bound together, and the definition of how weak or strong that attraction is, we define as being able to break up agglomerates with moderate amounts of energy, such as ultrasound or compressed air. Aggregated particles are much more strongly bound. A lot of times they'll look like grape clusters, and these cannot be separated through moderate levels of energy. Typically, if you're going to really hammer away at them, you run the risk of breaking them, not necessarily separating the particles, but just cleaving them. And quickly, here's the sort of 10,000-foot view of what the particle interactions are like. I guess that's no pun intended. But attractive forces are always competing with the repulsive forces. On the repulsive forces, more often than not, are coming from some charge on the molecule. And the idea is that to get them separated, we want to basically make it less... Sorry, excuse me, there's someone at the door. We want to do something to separate them, something to overcome the charge attraction. So we might, if we were in a wet dispersion, start adding surfactant to coat the particle surface. Or in a dry dispersion, we might try and find the right amount of compressed air to apply. And this is sort of a for-your reference slide. It's just illustrating basically the previous slide, which is at some distance the particle the potential energy of interaction between particles comes down to some manageable amount. So when we're talking about dispersing particles, a lot of times we are operating from some theoretically ideal basis. And that basis is that we have large particles, large agglomerates, when we have no energy to separate them. We start applying more and more energy, and then hopefully we get to some stable region where we fully disperse the particles. And then as we add more and more energy, we begin to physically start breaking the particles. That's the theoretically ideal case. Most of the time, it's very difficult to find those plateaus. You can find them with some materials that are just very well suited to that, but more often than not, you're breaking the particles at the same time as you're deagglomerating them. And that's unfortunate, but it's the real-world scenario, so we'll give you a few, I guess tips is the right word for it. We'll give you a few tips to know when you've reached the correct amount of energy, in this case compressed air. So again, just another way of thinking about it. Theoretical, we go from agglomerates to perfectly well dispersed to breaking the particles. But in the real world, the breaking is happening at the same time as the deagglomeration. How that might look in your particle size distribution result is if we were just dispersing agglomerates at low pressure, in this case 1 bar of compressed air, we have a distribution that has a pretty significant coarse mode. Right, that's this peak right here. As we increase the compressed air pressure to 2 bar, that mode begins to disappear. Now it looks a little bit more like a shoulder. And as we move to 3 bar pressure, the mode almost entirely disappears, and it looks more and more like a Gaussian distribution. Or at least this main mode does. So this is a very strong indicator that these larger particles were agglomerates, because as I'm increasing the air pressure and not changing any other measurement condition, the particle size is reducing. On the flip side, we also want to be aware of breaking particles. And that's simply the case here, and it's maybe a little difficult to see. It certainly isn't leaping out, but then most examples don't. In this case, we've increased the air pressure from 1 to 3 bar, and the 3 bar result is the red result. And what we've seen here is that although the largest particles are still decreasing, so we're still removing the largest particles from the measurement, we are forming new small particles. And that is usually an indicator that we're beginning to break the particles. So this is something we want to avoid. In this scenario, I might choose 1 or 2 bar simply because they're ending at around the same place. Their finest particle sizes are roughly the same, and they're not forming new small particles. So now we'll move on to how you might use the PowderJet to do all this. And real quickly, if you've never seen it before, here's the PowderJet accessory. What this is a cover that flips open, and as you can sort of see in the image here, there's a bunch of stainless steel components. If we look at the top, what we have is a vibratory feeder, a hopper that you can choose to use or not, where you put the sample in the hopper, and then we usually have some attachments somewhere in the feeder tray to help basically distribute the powder flow across the whole width of the chute. The powder flows down the chute, we're vibrating it down the chute, and then it falls into the measurement zone. So as it falls down the chute, what we're actually doing is we're passing it through a Venturi nozzle. And the Venturi nozzle is where the compressed air comes in, and we deagglomerate the powders in 360 degrees. Ideally, the powders are fully dispersed. They travel down the measurement cell, through the measurement zone where we have the red laser coming in, and then they're evacuated through the bottom of the system into a vacuum that's sitting underneath it. If we were to zoom in on the Venturi nozzle and the dry cell in general, what we would see is that when the compressed air comes in through the side, it's being accelerated through the Venturi, and the system was designed so that the air, the compressed air, is reaching Mach 1 velocity. So quite literally, it's sort of miniature sonic booms that are happening inside the system. And it's actually pretty neat. Sometimes you can hear it. If you get real close, you can hear it sort of sounds like a gurgling sound, but not quite as round. So we introduce the compressed air. It's accelerated based on the geometry of the nozzle. It's dispersing the particles, and then as they flow through the system, we're also pulling in just normal air. So not through the compressed air line, just the ambient air. We're pulling it through these laminar sheets. So it's really just sheets of metal that we have stacked, and the idea is we want to create a laminar flow of air. And that's basically to protect the cell windows. If we're running very abrasive materials, very abrasive samples, it's possible that given enough time, enough of the abrasive particles might interact with the cells that they might begin to scratch. By having these laminar air flowing along both cell windows, we basically do a much better job of keeping the particles away from the cells. And what that essentially does is it keeps the cell cleaner longer, and it also reduces the cost of having to replace damaged cells. So this is a very nice sort of refined design that we implemented with the PowderJet. Two other things to draw your attention to is that there are no impaction surfaces in the PowderJet cell design. And that's important because every time you introduce an impaction surface, and you can think of that quite literally like shooting the powder at a wall, every time you have an impaction surface, the chances that you're going to break your particle go up. It's the most effective way we know of to break particles. The other thing is that with the compressed air being accelerated to near supersonic, sometimes supersonic velocities, we actually, it's more than just a neat thing to say. It actually improves dispersion because there's a phenomenon that happens called the formation of a boundary layer. So you can think of you're shooting air molecules at a wall. As the air molecules get closer and closer to the wall, there's going to be a buildup in local pressure, and the air is sort of going to, it's not going to hit the wall, not all of it. The air molecules that are being shot at the wall are going to hit this boundary layer and then sort of spread out, right? It works the way with most fluids, and by reaching these velocities, we're effectively ignoring the boundary layer. So the particles, as they collide with themselves, they're not sort of slipping by themselves, they're not sort of hitting their own boundary layers, they're ignoring it because with the supersonic flow, they're not given enough time to realize the boundary layer is there. That's a very non-technical explanation, which is the most I'm capable of at this moment, but that's essentially what's happening. So it's more than just a neat thing to say that we're at Mach 1 velocity. It's actually very useful for the dispersion. And right at the top of the slide, I called it rocket science because it is actually sort of like rocket science, right? If you were designing a rocket, a lot of these same considerations is what you'd have to think about. And I promised one of our design engineers I would say it. So again, the reason we care about the dispersion mechanism so much is because we want to get closer and closer to this ideal state. And we do that through different considerations like having no impaction surfaces. That helps us stop the onset of comminution and breaking. So I'll spend a little bit of time talking about this feature in the PowderJet called the auto measurement button. And this is a very nice feature because in a lot of ways it's one button operation, and it sort of turns on many of the different components with the 950 and then turns them off when the measurement's finished. And it boils down to three different choices. So in order to set up the auto measurement function, we need to decide what begins the measurement, what to do while the measurement is happening, which essentially boils down to what scans are good and how do I get more good scans, and then what stops the measurement. So here are a bunch of screens from the 950 software. I'm going to try and highlight different things, make them bigger. So in this measurement tab, we have a few different things that we're seeing. The first is this data acquisition times. This is just the number of measurement scans we want to take. We can possibly use this as a stop measurement condition. It competes with one other we'll get to in a slide or two. The number of blank scans really isn't all that important. You could put it at a very high number or a very low number. Because the system is so stable and it's self-cleaning, a lot of times we don't have to take multiple blank measurements. Just the first one at basically any condition is going to be suitable. And then we have this transmittance range up here, and this is all it is just a visual guide. When you take the measurement and you're looking at the transmittance bar, which measures how much of the laser light is passing through the cell unscattered, There's a green bar to the next of that transmittance indicator, and that's just a visual guide for the user. So not too important in this context. If we move over to the System Preparation tab, we have this top area called Configuration to Stop After Measurement. And all it really is you decide what components get turned off after the measurement is complete. Generally, when we run this in our applications lab, we'll leave all three of these checked on. And the idea is you don't want to leave the vacuum and the compressed air on after the measurement's complete because, to be honest, they're a little loud, just as loud as your vacuum that you use in the house. And it's just it's nicer to have them off. The next box is the Auto Measurement button box. And what this is what components are turned on when you're acquiring the blank. So when you click the Auto Measurement button, it'll automatically turn these things on, so in this case the vacuum and the air. It'll acquire the blank, and then it'll begin feeding the sample and acquire the measurement. Most of the time we leave vacuum and air turned on. You can choose not to. Sometimes it doesn't make a difference. The next box is a big one. It's called Sampling Condition, and there's a few important things here. This T% for sampling is actually very important, and you can think of this as sort of a data filter. So every time we take a measurement, for a dry measurement, the minimum number of scans we can acquire is 1,000. Let's just say that it's 1,000. Each of those 1,000 scans represents an individual snapshot of the 78 detectors we use during a dry measurement. Each of those scans has an associated transmittance percentage. What we want to decide here is, do we want to turn this data filter on and not count any scans outside of this transmittance percentage range? A lot of times we like to have this on in the lab because it really helps improve precision. We can sometimes use what we're calling the start trigger. This is one possible start condition that uses the intensity falling on a detector, which we also call the sensor here. The other possible start condition is simply you click the auto measurement button, and when the measurement sequence begins, it starts collecting scans. That's the one we use more often. I'll get into why, I think, in a few slides. And then the stop trigger. So along with simply reaching the maximum number of scans when we were in the measurement tab a few slides back, the other possible stop condition is the stop trigger. And what that does is it waits for the transmittance percentage to get above some certain critical level. And that's user definable. A lot of times we'll set it at 99 or 99.5% transmittance. And what we think that means, what we hope that means, is that there's no more sample left on the tray. All the powder has fed into the measurement, therefore the measurement should end. With some cohesive materials that aren't very free-flowing, so if you imagine like bread flour, because they're not free-flowing, a lot of times when you use the stop trigger, you'll click this to yes, and then you'll say stop after waiting some amount of time. Because as you can imagine with bread flour and some cohesive materials, you might get a sort of big collection of particles to fall off the chute, and then you might have a gap behind it, and then the next big collection of particles comes after that. So having this little delay time in there helps prevent premature stops to the measurement. The next area is feeder speed. And this is all about how we're feeding the material into the measurement zone. So the speed really represents the starting speed. So 100, it's on a scale of not quite 0, because it doesn't make any sense to start off at no speed, but some very small value up to 200. So the starting speed can be kick-started by this initial coefficient. So let's say you have some powder that's been in the tray for I don't know how long, or it just very easily compacts and sort of settles in. You might want to increase this coefficient here, and what this does is it multiplies the starting speed. So in this case it would be 120. So you're starting at a faster speed to sort of get the powder up and moving, right? You're overcoming the coefficient of static friction. We can choose to automatically control the speed, or we can choose to leave it at a fixed speed. Almost always we want to leave this on automatic, because what that does is it turns on a really good function called the feedback control loop. And the reason that's very good is when it's on, we can give it some target T% to hit. So in this case, it's 97%. And what the system will do is it'll speed up or slow down the powder feeder so that it can hit this target T%. And when this target T% is used in conjunction with the T% for sampling data filter from a slide or two back, what it essentially means is that precision becomes very easy to obtain. Very high precision is very easy. We can choose how quickly the feedback loop refreshes. Most of the time we just leave it on medium. It's not too important, but it's something that we can change. The final box is air. And this is where we choose the level of compressed air we want to use. So everything from 0.01 megapascal to 0.4 megapascal, which is a range of essentially 0 to 4 bar. And we want all sorts of different control over it. We can choose it in any of 40 levels because the air pressure we choose greatly affects the dispersion we can obtain. And yes, we know that there's a typo in the software. It frustrates us. We're trying to get it fixed. So in summary, there's two ways to start a measurement. We can either begin collecting scans immediately. This is typically what we do in our own applications lab. There's really not many downsides to it. Or we can wait and use the start trigger, which essentially waits for the powder to start flowing through the measurement cell, and once the scattered light on a certain detector reaches some critical threshold, we begin collecting scans. I'd advise you to take care that when you're using the stop trigger, that the amount of powder you load on the feeder tray isn't too far back, right? So if in this image here we're putting all the powder in the very back of the feeder tray, the stop trigger might actually trigger before it feeds all the way up to the front. We have two options to stop a measurement. We can either do what I'm calling a timed measurement, which really just uses the number of scans you select, or we can measure all the powder on the tray, and that is essentially the stop trigger. Typically, we'll use both, and it's determined by the sampling. So if you have a very easily sampled material, then you can do the timed measurement. If you don't have a very easily sampled material, you'll probably want to use something like a spinning riffler or a chute riffler, and then measure the entire pie slice. So everything that you put on the feeder tray of the PowderJet you want to measure. That is the most surefire way of getting high precision results. And I'd also advise you to take care when you use the stop trigger, try and build in some delay, right? So again, in the case of the bread flour, if you have a sample that's sort of breaking up or separating on the feeder, you don't want the gaps in between to activate the stop trigger and stop the measurement. During the measurement, we want to decide, do we collect all the scans or only what we think of as the good scans? A lot of times that T% control, the thing I referred to as the data filter, greatly improves precision. And the reason you'd want to use that is if you felt very confident or could prove with something like an optical microscope that you didn't have very large single particles or very large aggregates, right? If you knew very well that you had only agglomerates in your sample, probably because it was a very cohesive sample, something like that, you don't want to include the agglomerates in your particle size distribution. Especially, you don't want to do that if your goal is to disperse it down to its primary particle size. And historically, that's been one of the most pressing challenges of dry powder measurement is how do you get a result that looks like the wet result? You know, in the wet result, a lot of times you won't get the agglomerates to show up because you can get rid of them with the application of ultrasound and by modifying the dispersion conditions. So the way we've done it with the PowderJet is we acknowledge the fact that it's really difficult to control the mass flow rate through the cell. And sometimes you're going to have these big collections of particles, possibly agglomerates, possibly the bread flour sort of chunks, come through the measurement zone. And because we can't disperse everything in the split second the material is passing through the dispersion nozzle, we're just going to ignore those scans. We say we only want to collect information between this T% and this T%. We know that anything outside of that is either not enough material for a statistically significant scan, or too much material because agglomerates are coming through. So a tight range usually leads to the best precision. But again, there's a flip side, and here I would advise you to take care that very agglomerated powders, if your T% range is very, very tight, very agglomerated powders can be very easy to miss that range. So when you're starting off method development, keep a wide range and then tighten it up as you take more measurements and fine-tune the method. And then you have to choose whether or not you want to use the feedback control loop to control the speed of the vibratory feeder. I can tell you we always use this in our lab. It's a really nice feature. We're really happy to have it with the LA-950. And again, I just advise you to take care that the target T% you set up for the feedback loop is within the T% range for good scans that you might set up above. If you're only collecting measurement scans within the range 98 to 95% T, and your target T% down here for the feedback loop is 90% T, you're going to exhaust all your material and not get a measurement out of it. So it's something to take care of. All of these things add up to what we feel is actually a really nice accessory that removes a lot of the historic headaches from doing this measurement. And it really boils down to the feedback control. This is a very critical parameter. As far as we know, we're the only people that have implemented it, or at least implemented it in our specific way. And when it's done really well, this is how we get the maximum precision. So if you sent samples into our applications lab for dry powder analysis, we're almost always going to be using this feedback control because it's how we get the best looking data. And because we can very finely control the mass flow through the system, what it also practically does is it removes the chance of any ghost peak showing up. That's historically been another challenge with dry powder measurements is some systems, not always HORIBA, in fact most of the time not HORIBA, can generate ghost peaks or, without getting too far into it, what I would just call funny business, where the distribution doesn't look right, it might be shifted funny, just different things. Controlling the mass flow rate to such a tight degree really removes a lot of those headaches. The fact that we're using near supersonic compressed air speeds really helps with dispersion in a lot of ways, as I discussed. And the auto measurement just makes the whole system easy to use. You can't really improve on one-button operation. So next we'll move on to certain method development considerations. Let me see how I'm doing on time. Still okay. So here's the general dry method workflow. The first thing we want to do is get the sampling right and determine the refractive index if we need to. For more information on the refractive index, I direct you to the third lecture in our boot camp series. And we also, just I think in December, Mark Buemiller gave another webinar about how to optimize refractive index selection. The short version for us today is simply if your material is below roughly 40 microns, we need to worry about refractive index. If it's entirely above 40 microns, we don't need to worry at all. So once you get the sampling right and lock down your refractive index, next we'll want to measure at 3 different compressed air pressures, typically low, medium, and high. It's not so meaningful if you do very high, less 1 level, and very high, less 2 levels. And then from that data we're going to determine the optimum pressure based on what the graphs look like, and with specific attention to the D50, D10, and D90 parameters. We'll want to make sure that we're de-agglomerating the big stuff without breaking particles. We may also take it an extra step and try and compare wet and dry measurements. It's generally true that if you can get a good wet dispersion, the best possible dry data you can get is equivalent to that good wet dispersion. We might adjust some other settings like the initial sample feed rate or the feedback response time to improve precision further. We can decide to measure all of the sample on a tray, or we can decide to get multiple measurements off the same sample loading. But once we have all that locked down and chosen, then we want to test reproducibility. So multiple measurements, and then we compare the measurements to see how tight certain things like the coefficient of variation are. So very quickly, goals for any method. The first goal is the most important. It should be reproducible and something that tracks product or process performance. So if it's not giving you any actionable information or anything that can be useful for you or potentially your customer, then it's probably not the right method to be using. You might have other goals too. We're going to focus on precision, but you might also want the most accurate result possible. That can be a little bit tricky, and for more information on that, I direct you to the Method Development Bootcamp lecture. It's the 6th lecture. Otherwise, it's repeatability and reproducibility. For a dry measurement, all we really focus on is reproducibility because we don't capture the dry powder as it flows through the cell and then recycle it multiple times. Every measurement is a new aliquota sample, essentially, so it's only reproducibility. We could talk about resolution or the need to match historic data. Again, more information in the Method Development Bootcamp lecture. We'll want to use a structured approach that helps explain any decision or choice that might influence the result. We'll want to document that, have data to support the selections made, and so that other people can understand what we did. And real briefly, I'm sure you all have seen something like this before to explain the difference between accuracy and precision. This is always the ideal scenario. You have high accuracy and high precision. But in many times, we're happy to just have high precision, right? We want something that's reliable and that, if necessary, will show differences in either changing processes or changing product quality. And the basis for any reliable data is reproducibility. So I know I'm hammering this, but it's because it's the most important thing. And reproducibility is where you prepare the sample, measure it, empty the system, and repeat the whole process. And good reproducibility is laid out by various standards. So if you're in the pharmaceutical industry, you might look at USP 429, which lays out good reproducibility as having a coefficient of variation less than 10% at the median and less than 15% at the D10 and D90. And this is based off of a minimum of 3 measurements acquired from unique samplings. If you're not in the pharmaceutical industry, you might want to pay attention to ISO 13320. This sets the COV limits at less than 3% and less than 5%. And an important note is that if your material is less than 10 microns, all of these limits double, which is an acknowledgement that smaller particles are more difficult to disperse and therefore more difficult to get good precision on. Now, the 950 software automates a lot of these coefficient of variation calculations for you. In this case, if we were looking at the ISO 13320 guidelines, we have our 3 reproducible measurements. 3 different measurements. It's automatically calculating the average for the D10, D50, D90, the standard deviation, the coefficient of variation, and then it's giving you a visual indicator if it's passed on the D10, D50, or D90. This is, to our knowledge, a unique feature in the LA-950 software, and we have more information on how to use it in Technical Note 169. So on to some case studies. This is magnesium stearate. It's a very common pharmaceutical excipient. And it's only one measurement we're showing here, one measurement at 3 different pressures. And what we want to decide, and it's difficult to tell just by looking at this result, but we want to try and figure out which is the most appropriate air pressure to use. One way to determine that is to look at the D90, D50, and D10 at different air pressures. And like I went over a few slides back, we're always hoping for the ideal scenario where we find some plateau in dispersion. That's not the case here. So what instead we'll focus on is how reproducible the measurements are at different air pressures. So 4 measurements of magnesium stearate at 3 bar pressure gives us COV values at the D50 of nearly 1.5, the D10 below 1, and D90 at 2.2. These are all passing values, no matter what standard you're looking at, all excellent values, but maybe they'll get better as we change the air pressure. And sure enough, as we go to 2 bar pressure, the COV values drop to 0.28, 0.24, and 0.89. A significant improvement on the 3 bar results. And then we check the 1 bar results just because we want to test 3 different air pressures. And still, really excellent results, certainly passing, but it's clear that the 2-bar result was the best in terms of minimizing our coefficient of variation. And that provides us with enough justification that, in the absence of any accuracy measure, if someone were to ask us why we chose the 2-bar air pressure, we could say because it minimized the coefficient of variation and was therefore the most precise result. If we do the same sort of study with microcrystalline cellulose, and do the same thing where we graph D90, D50, D10 against changing air pressures, we'll see that maybe this is a plateau, right? We see that the data doesn't really change. The size distribution doesn't change too much between 1 and 2 bars and begins to decrease at 3 bars. If we go through our reproducibility test where we're monitoring the coefficient of variation, at 3 bars, again, everything's passing. It's excellent data. D50, D10 are both below 1%. The D90 value is at 2.6%, which a little higher, but still really good. I must have gotten rid of those slides. I apologize. But the process is the same. You would do the same thing at 2 bar and 1 bar, or whatever other air pressures you measure at. We say, we recommend at least 3. It doesn't mean that you can't do more. In this case, we can also measure the microcrystalline cellulose wet and compare it to the dry measurement. And in this case, the wet measurement has slightly smaller D90 values, so we could say that it's a little bit better dispersed. And the dry value has a little bit higher D90 measurement, so maybe not quite as well dispersed. D10s are very similar, 22.4, 22.6. D50s are very similar as well, 59.9 and 59.0 essentially. If this weren't microcrystalline cellulose, which we know isn't very dense, if instead it was a very dense material, we might flip it, flip the explanation and say that the dry is actually a little bit better dispersed, simply because with very dense materials you always have to worry about the largest materials falling out of suspension. So you'd start looking at the density contrast between the material and the liquid dispersant, and that could be a good enough reason to measure dry. A few quick slides on different applications that show some of the dispersion performance of the PowderJet. Here we have titanium dioxide dispersed almost entirely submicron, which is a very difficult thing to do with TiO2. It's a very strongly, tightly agglomerated material. In this case, though, we're getting excellent dispersion performance. Now, I'm not going to say that you could just take any kind of TiO2, dump it in the PowderJet, and get this kind of performance out of it. We generated this in our applications lab, and it's because we have enough experience with the unit to know how to set up the things like the T% filters and the feedback control loops. But it's very possible. This isn't an arcane science by any means. It's just something that we've arrived at because we have a lot of experience with it. I'm also going to show here some Zirconia data. This is dry data acquired with the PowderJet. And what we're seeing here is that the Zirconia is showing a separate mode, submicron mode. And the question back from the prospect was, is this real? They had had experience with another manufacturer who routinely reported ghost peaks with a lot of their materials. And they said, we want to know, is this real or not? So what we did then is we dispersed the same material in water, and we still saw the submicron peak. It was shifted a little finer in the wet analysis than the dry. And here I overlaid the two. So the wet analysis is the blue and the dry is the red. And our explanation is that the dry system only can use the red laser inside the LA-950. We don't make any use of the blue LED at all, and there's a lot of reasons behind that. The wet analysis does, however, make use of the blue LED, and the blue LED is at 405 nanometers as opposed to 650 nanometers for the red laser. And as you drop the wavelength, generally you become much more sensitive to small particles. So in this case, we trust the wet value much more because we can use the shorter wavelength blue LED. And we don't necessarily expect perfect overlap here simply because it's right around 100 nanometers that we really begin to see the limitations of the red-only laser measurement. So the dry system will begin to sort of peter out around 100 nanometers, and in fact that's where the specification ends for the PowderJet, is at or near 100 nanometers, whereas the wet measurement system goes down to 10 nanometers. So in this case, if the customer chose to measure wet, they might get a more accurate analysis for the submicron particles, but it's going to take a little bit more effort than measuring it dry. The PowderJet also works excellently with very large particles. So here we have some 3 millimeter alumina balls that we measured during the development of the 950 PowderJet. And the median diameter here is 2,700 microns, and I know it's a little bit difficult to see, but the distribution is actually going off the edge of the range. So the median comes in just underneath, and it's quite literally the bleeding edge limit of the LA-950. If we looked at coffee results, we see different types of coffee. This could be a finely ground, maybe some espresso here. We get into the medium grinds, a little bit larger grinds. The coarsest grind here actually has data that extends well over 2,000 microns, which had been the limit before the LA-950 was introduced. 2 points I'll make here before I move on is simply that to get really good data at large particle sizes, and for laser diffraction, everything over 1,000 microns or 1 millimeter is considered a very large particle, you need to have an exceptionally stable optical bench. If there's any flutter in the laser at all, you're not going to get good large particle data, and that's simply because all of the most interesting scattering for these large particles happens at very, very low scattering angles. And if you have a laser that flutters just a little bit, you're not going to get the accurate scattering information on those low-angle detectors. In the 950 PowderJet vertical design, basically means that the powder is flowing vertically through the cell as opposed to horizontally. Essentially means that there's no density limit when you want to measure dry. A lot of horizontal systems really begin to suffer when you have very dense materials because they'll begin to just settle out and stick on the horizontal tubing. And this is a shameless slide about the LA-950, I admit that, but it's important to talk about nonetheless. We really like the 950. We consider it the performance leader for laser diffraction. A lot of our users consider it the same. We really love to go head-to-head with other instruments that make outlandish claims because we can back them up. It's the 9th generation of the laser diffraction series of analyzers from HORIBA. In our experience, it's been incredibly durable. We use long lifetime components. The quality of manufacturing is very high. And that's shown up in the fact that we've been selling this instrument for nearly 7 years now and not had a single major failure in that time. It really, to be honest, it doesn't make our service department very happy because it's nice when you have an instrument that needs some regular attention to keep it working correctly. It gives them a lot of things to do. But it tends to make our users even happier because they don't have the headaches of having a lot of downtime with their instrument. Because of that, it has the lowest total cost of ownership. Other than the PowderJet, we can measure all sorts of different types of samples. We can measure suspensions, emulsions, even some pastes and gels with a unique accessory called the paste cell. And it has a very wide range, so everything down to 10 nanometers up to 3 millimeters. And that's the end of my presentation. For more information, we have a wealth of information at our website, horiba.com/us/particle. You can always contact us directly if my email address is difficult to remember or spell, because my last name is difficult to remember and spell. I would encourage you to contact us at labinfo@horiba.com. There's probably 6 or 7 of us that get that email, so it's literally impossible not to have something followed up on. And I would also say visit our download center. You'll be able to find this recorded webinar, all of our other recorded webinars, all of our application notes, brochures, technical notes, everything under the sun we throw up at the download center. So now I'll stop and I'll ask Jeff if there have been any questions that come up.
Well, there has been questions, and I'd like to invite people to go ahead and start typing questions in. I'll pass them along to Ian as they arrive. So the first question, which actually came in quite a while ago, is a customer has iron oxide with sizes of about 2 microns and asks if the dry application is suitable. So I guess we're looking at rust.
Yeah, yeah, the application should be very suitable. A lot of times what sort of eliminates the PowderJet from consideration, or any dry measurement, is when you have nanoparticles that are too small to be detected with nearly every system, when you have particles that are too large, or when you just don't have enough material. Generally, it's true that you need more material to measure dry than you do to measure wet. So, you know, the formulation, chemists out there, sometimes even though a dry measurement may be easier and more preferable to perform because they're, you know, synthesizing on microgram scales as opposed to milligram scales, they're forced to measure wet in something like our fraction cell or mini flow. But yeah, I can't think of a reason why it shouldn't work. It should be a slam dunk application.
Okay, great, great. Okay, now I have another question, although I know how you're going to answer it. Do you recommend conducting particle size measurements using an orthogonal method, such as microscopy, to show the accuracy of the results? And coupled with that, can the results be deemed accurate without an orthogonal method?
That's a very good follow-up question. The first question is yes, and there are really good reasons to always want to verify the accuracy using an orthogonal technique. And there are very good reasons beyond the fact that I work for an instrumentation company and my job rests on being able to sell products like that. But the very good reasons are simply that different techniques measure different properties of the particle. So laser diffraction is measuring something called the equivalent spherical diameter. So even if you're measuring a particle that's shaped like a pen, the 950 is going to represent the data as though it were a sphere of equivalent volume. Maybe not the most accurate data possible, but we have to make that assumption to make the mathematics workable. Now, you might want to use something like an optical microscope if the particles are large enough to verify and correct certain instrument conditions to improve the accuracy of the measurement. In fact, that's something that our friends in pharmaceutical are really good at. They will use a laser diffraction instrument because it's very easy to use and very quick and can handle a lot of different types of samples, but they will verify the accuracy of the results using something like an optical microscope. The really advanced, or at least higher throughput labs in pharmaceutical will have an automated solution like the PSA 300 that we have, which is literally just an optical microscope married to an automated stage controller and a software package that does the analysis for you.
Yeah. Yeah. If you ever visit our application lab, you would notice that there are several optical microscopes in the lab for exactly this purpose. When we start having questions, we reach for an orthogonal method. It just makes a lot of sense. Okay.
Yeah, and I should say too that for submicron particles that maybe are more difficult to detect using an optical microscope setup, a good orthogonal technique is going to be a dynamic light scattering instrument like the SC100. You know, you could prepare the sample in such a way that you're removing all the particles larger than a micron that are more difficult to measure with dynamic light scattering, and that could be your orthogonal technique for those small particles.
Yeah, absolutely. Okay, another follow-on question. Are Stearins typically used to demonstrate system suitability? And I'm going to kind of summarize that question is what sort of Stearins do we recommend and what size ranges?
When you say standards, I'm going to say standard reference materials, SRMs. It's the nomenclature that NIST uses. It's the nomenclature that a lot of the manufacturers of these materials use. And I would say that, yes, we do use them. They don't have to be used. If you have an internal material that you feel very confident does not change over time and the manufacturing process is very stable, you could develop an internal standard that does the same thing. But you know, the easier solution, and a lot of times, is simply to purchase a standard reference material from a company like Thermo Scientific, A few years back, Thermo Scientific bought another company called Duke Scientific, and these people are experts at manufacturing polystyrene lattices and different polymers that have incredibly narrow size distributions and incredibly well-characterized sizes for the certificate of analysis. So that's one way to measure system suitability. Another possibility, those are monodispersed samples. They're really good at testing the optical bench and making sure that the optical bench works correctly. Another possibility is polydispersed samples. They're more difficult to come by because there are fewer manufacturers in the world. The company we really like and have had a very positive relationship with for years is called White House Scientific. They're located out of the UK, and they manufacture glass beads and some other materials. We use their glass bead polydisperse standards to do our quality checking on the LA-950, both the wet system and the PowderJet dry system. You know, for more information too, I should say we have a lot of resources on the website for system verification. There's a technical note. I think it's Tech Note 151, 151. We have a web page up on system verification. There's a lot of information to be found there, and 1 or 2 webinars as well.
Okay. Is it necessary to bracket sample measurements with standards at the end of the run, since the because the instrument calibration could drift during use?
No, that is not necessary, and this is this could be a very long-winded explanation. I'll try not to make it too long-winded. Laser diffraction instruments are not calibrated. It's a common misunderstanding. These instruments are designed to operate off of first principles, right? The scattering off of a particle is related to the size of the particle. That is not something that needs to be calibrated. It's what we need to do instead of calibrating the instrument is to verify that the instrument is still working correctly. If you take something like a White House PS202 standard, which is supposed to be between 3 and 30 microns, and you measure it, and the certificate of analysis has some certified value for the D10, D50, D90, along with some bottle tolerance, and you find that the instrument is measuring outside of those ranges, we won't fix the instrument by recalibrating it. What we'll do is we'll check to see if something's broken. The first check is to make sure that the instrument conditions are appropriate, that the sample has not been compromised in any way. And then, you know, the next step is maybe the pump is broken, right? If the pump can't spin correctly, it may be that the largest particles have fallen out of suspension. But the instrument doesn't really get calibrated. What we do with the instrument at the point of manufacture is we will run certain standard reference materials through it to characterize the stray light scattering in the instrument. Because we're not selling these instruments at $1 million a pop, we can't put stealth absorbing material inside the instrument to take care of all the light scattering we don't want, you know, off of the cell surface, off of different components. So we try and characterize that sort of baseline stray light scattering. That is kind of like a calibration. We want to characterize it very well so that we know to remove it from every measurement after that. But that won't drift.
Okay. All right, next up. How do you know when your method development is mature? In wet dispersion, there seem to be lots of variables, sonication, recirculation, and so on. What are the most important parameters in dry dispersion?
The cop-out answer is precision. If you can get a result that has a very low coefficient of variation, if you can use a method that produces results that have very low COV values, certainly lower than the ISO standard, you can feel fairly confident that's a good method. If you get a result that, when you look at the particle size distribution graph, doesn't seem to make a whole heck of a lot of sense, then that's cause for concern. When I teach our boot camp training course, I always tell people, you know, we can look at the statistics that come off the instrument till our eyes bleed, and if we never look at the particle size distribution graph, we could be missing the most important information possible. Right? If all we want to do is minimize some value or maximize some other value, but the graph itself looks funky and unrealistic, then we're chasing our own tails. But anyway, to get off that digression, a method is mature simply when you have very precise results and when you can feel relatively confident it's giving you accurate results. You know, it's hard for us to say that a tweak in a method that moves the D50 from 30 microns down to 28 microns, we can't tell you that that's better if you're using a microscope and the microscope says the D50 should be 28 microns. I would say that's an improvement in the method. You know, but otherwise it's precision and it's being easy for multiple people to use. You know, if multiple operators can generate the same data without having to cherry pick, you know, the best 3 results out of 100, right? That's a very good method.
Okay. Where can I find more information about RI on powders?
The actual refractive index values, there's a few different locations we could point you to. We actually list them, I think, in the refractive index webinar. It's the 3rd bootcamp webinar. Without going through them, a lot of them are URLs or handbooks. Without going through them right now, I just point you in that direction. Or you can send Jeff or I an email and we can send you the list. But there's a few different places to look.
Okay, and how would you test a clay soil slurry sample with this device while ensuring that the entire sample flows through the hopper?
We probably wouldn't use the PowderJet to measure anything someone's calling a slurry. It needs to be purely dry, or at least dry enough that we can disperse it. You know, if you run anything wet through that, you know, Mach 1 velocity dispersion nozzle, you're going to, the system's going to get very dirty very quickly, and that's going to be a bad day. Now, if we're talking about measuring it wet, then, Jeff, remind me, the question was about how do you know that you're getting all of the particle sizes?
No, you want to test a clay soil slurry, and how do you ensure the entire sample flows through the hopper?
Yeah, okay. So, yeah, probably not. You know, it could be that I'm just missing some subtle point of your application, and if that's the case, feel free to email me and we can continue talking about it offline.
Yeah. Okay, well, I think that about wraps it up. So I'd like to thank everybody for their attendance, and, well, we look forward to hearing from you. Keep an eye on our email newsletter for announcements of future upcoming webinars on various particle sizing topics. And we may see you at PitCon. If not, we'll see you elsewhere. Okay. Thank you, everybody.
Thanks everyone for showing up and for the baby name possibilities. That made my day. Thanks, everyone.